Figures 7.9 through 7.11, card.java, deckofcards.java, and deckofcardstest.java. In this example, we're going to create a card shuffling and dealing simulation, and there's a couple of interesting aspects to it. First of all, we're going to see for the first time in the examples that we've been doing more interactions between classes, but also we're going to be creating an array of a non-primitive type, which gives us a chance to discuss some other issues that can be called gotchas, if you will, for people who are new to Java programming. So actually what I'd like to do first here is take a look at the test application so that you can see what it is we're trying to do. We'd like to create a deck of cards object. We'd like to then shuffle the deck and deal out all the cards. So we're going to build into our deck of cards class a shuffle method to shuffle the cards, and this little loop's going to loop 13 times, printing 4 cards at a time to the command line, and it's going to obtain each card by calling the deal card method, which we will then get back an actual card object and convert it to a string for output in these %-20s fields. And -20 indicates that we want each card to appear in a left justified field of 20 characters. Now if I go ahead and run this program first so you can see the results, here you can see 4 columns of output, 13 lines of output, and if you read through the card names you can see that they clearly were shuffled. As you'll see when we first create the deck, we have all of the cards in order for one suit, followed by the next suit's ordered cards, followed by the next suit's ordered cards, etc. So we'll take a look at that initialization code in just a moment. So we'd like to manipulate this deck of cards, but before we can have a deck, we have to have something that represents the concept of a card, which is our card.java file. And you can see here that we've defined a public class called card that has 2 private instance variables, both of which are strings, the face and the suit string. And we're going to initialize those via the constructor for class card, which is defined here down at lines 10 through 14. Now, a thing to keep in mind about the concept of a string in Java is that Java strings are not primitive values. They are objects, so the variables we're declaring here are initially reference variables that don't refer to any strings yet. So they normally would get the default value null, lowercase n-u-l-l, unless we provide a constructor that's going to assign values, as we do here, to the 2 different instance variables. So each card will be initialized by the deck of cards. And then separately we have a new feature here, which is something called the toString method. And this is actually a special method in Java. It turns out everything in Java has a string representation. So Java already knows how to take any primitive value and display it as a string or treat it as a string. And for any new class type that you create, if you define a toString method that looks exactly like this one on line 17, then this method can be used to convert objects of your class into a string. And in fact, even if you have no need to do that, it's still a good programming practice to provide such a method, because you might want to use it in logging error messages that occur during a program's execution. So as a worst case, if you have no specific need for this method in your class, you might still provide it to give back a string representation of all the data in a particular object of your class at the time that an error occurs, so that you can log that information for debugging purposes. Now in our case, this toString method is going to return the following string, and I'm using some string concatenation here with the plus operator. I have the string face plus the string literal consisting of space, and I add it to the end of that the string suit, and now I have a string representing the complete card information. Now it turns out when you add anything to a string, an integer, a double, any object, when you add anything to a string, the anything part gets converted to a string automatically by Java. So for example, if I wanted to output the sum of a bunch of values, I could output the string sum is plus the sum variable, which would presumably be some numeric type, and it will convert the numeric value into a string and concatenate it for me automatically. So this is kind of an interesting capability. Now the question is, where in the world is this functionality defined that lets any object be converted to a string in Java? Well, it turns out that when you create any new class in Java, you are never building your class from scratch. You're actually implicitly inheriting or extending from a special class in the Java lang package, java.lang package, called object, which is the most fundamental class in all of Java. So I'd like to take a quick look at that class in the online documentation here. I did mention that the Java lang package is where you'll find the object class, so I'm going to go to that package. And it's in this package because it is the most fundamental class in all of Java. Here it is. And here's the overview of class object, and the most important part is what methods we get for free simply because we are creating a class in our Java programs. And it turns out that we get the methods shown here for free. We have a concept called cloning of objects, which you can make a copy of an object using the clone method if you define how to clone objects of your class. We have an equals method used for testing to see whether two objects are equal, and again, you often have to define how to do that comparison. We have a finalize method, which we'll talk about in the next lesson, which has to do with garbage collection. When you create objects inside of a program in Java, you've probably noticed that we say new a lot to create the objects, but we don't actually ever remove the memory. The garbage collector's job is to do that, and finalize is part of that garbage collection mechanism. Get class. This is interesting. Every single object in all of Java knows its own class type, and that can be used to do some very interesting and powerful programming because you can dynamically discover information about an object and invoke methods of an object and create new objects as well. So Java has a concept which is called introspection and reflection that allows you to do things like that. Every object has a hash code function or method. It turns out that if you're using hash table data structures, you can use pretty much any object in Java as the key in a key value pair of information. Notify, notify all, and the three different wait methods down here all have to do with multi-threading, which is beyond the scope of this video course. And the most important thing for us right now is the toString method, which I'm going to click, and you can see public string toString empty parentheses, the exact same first line as I showed you over here in my code. What we are actually doing here in our code is redefining, or what we call overriding, the original toString method, which is defined in class object. And the original toString method actually outputs the result of this expression, which basically says display the name of the class, an @ character, and a hexadecimal version of the hash code for the current object. And that string representation is not very useful, especially if we want to output the string that represents a card of information. So what we've decided to do instead is redefine how toString works for our card class, thus basically replacing the toString that we've gotten for free. And instead we're going to return the word face, not the word face, but the value of the face, the word of, and the value of the suit as a combined string of information. So this is our card class that will be used to represent the individual cards in a deck of cards. And now we're going to create 52 objects of this class in the deck of cards class. So let's take a look at the deck of cards class. You'll notice once again that we've imported the java.util package's random class so that we can do some random number generation. We're going to use that to help us with the shuffling algorithm. And we also have a bunch of instance variables in our deck of cards class. The key one being this deck array. It's a one-dimensional array of type card. So you're obviously able to store values of any type that you wish in an array, and in this case we're going to store cards. Now A couple of things to point out about what we're doing here in Java. First of all, recall that we are not specifying how many elements are in the array yet. We are simply saying that the variable dec represents a one-dimensional array of type card. We have not said how many cards there are yet. Separately, once we create the array, that simply creates references to cards. It doesn't actually create card objects. So all of the elements of the initial dec array will have the value null, and then we will first have to go create each card object and place it into the array. So we'll talk about that more in a moment. We also have a private integer called current card that keeps track of the current card for dealing purposes. We have a private final integer called number of cards, again in all caps because final variables typically represent named constants, and we have 52 cards for the purpose of this example. And we've declared a random object called random numbers that we'll use for random number generation. Now, when we create a new deck of cards, our constructor here at line 13 will be called, and we've declared a couple of local arrays of type string, one called faces and one called suits, and we've used the array initializer list syntax to initialize each of these arrays. So for the faces array, we have 13 elements representing ace through king for the given set of cards, and then for the suits array, we have the 4 different suits of a typical deck of cards. At line 19, we finally create the actual array of cards, and dec is the array of type cards, so we actually assign it a new card array of number of cards elements. That's 52, of course. We set our current card equal to 0, and actually line 20 is unnecessary because the simple fact that current card is an instance variable will cause it to be initialized to its default value, which is 0 for integers. But we wanted to be explicit about it in this program that we want to start dealing from the index number 0 in our deck of cards. We create our random object called random numbers, so that we'll use that later to do our random number generation for the purpose of shuffling. And then we have a little for loop here that walks through every element of the deck array and one at a time assigns each element a new card object. All right, so you can see here that we're indexing starting at 0 as long as the variable count, is less than deck.length, which is the length of the array, 52 cards, so our indices are 0 through 51. And we've got a bit of a clever calculation being performed, actually 2 different calculations being performed here as we create each new card. First, as we call the card constructor, we pass one element of the faces array into the card constructor, and then we pass one element of the suits array into the card constructor. Now, the remainder operator that we're using here gives me the remainder after we divide count by 13. So for the first 13 values of count, the remainder is going to be a number from 0 to 12. And of course, the indices in a 13-element array, such as faces, are 0 to 12. Then when we get to the value 13 for the index number, 13 divided by 13 is 1 with a remainder of 0, so I start going back from 0 again through the faces array for the next 13 cards, and then I go back starting at 0 again for the next 13 cards, etc. Now, separately, we have the expression count divided by 13 here as well. Count is an int. 13 is a whole number literal, which is also an int, so the result of this expression is always an integer. And if the number that I'm dividing, the count value that I'm dividing by 13 is a number from 0 through 12, the result of this highlighted expression is always going to be 0. If it's a number from 12 to 25, it'll be 1, etc., etc. So for the first 13 cards, the value will be 0. For the next 13 cards, the value will be 1. For the next 13, it'll be 2. And for the last 13, it'll be 3. So basically what we're saying is that we're going to initialize the first 13 cards as the card faces ace through king of hearts. Then the next 13 cards will be ace through king of diamonds. Then the next 13 will be ace through king of spades, of clubs, and the last 13 will be ace through king of spades. So after we've done all of that work in the constructor, we now have an initialized deck of card objects. And in fact, it's really not a deck of card objects. It's a deck of card variables, each of which refers to one card object. Our shuffle algorithm is going to shuffle up those card variables to point to different card objects. We start by setting the current card variable to 0, and then we have a for loop that's going to iterate through every card in our deck, starting at 0 and as long as we're less than the deck.length. And for every card that I'm looking at, I'm going to pick a second random card from the deck and then swap those two cards. So if I'm looking at card number 0 in the deck right now, I'm going to randomly pick another index number, and the result of this expression is going to determine that index. randomNumbers.nextInt is going to produce a value from 0 up to but not including the value of number of cards, which is 52. So I'll pick a number from 0 to 51, which are the indices in my deck. Then I will take the first card I'm looking at, deck sub first, and assign it to a temporary card variable. I'll then aim deck sub first at the card that deck sub second is currently aimed at, referring to. And then I'll take the temp card and assign it to deck sub second, thus swapping the two cards. Then I'll move to the next card in the deck. So assume that the index is now 1. I will pick another random integer for a different card in the deck and swap those two. So as I walk my way through the deck of cards, I'm guaranteed that I will swap every card at least once with another card in my deck. After we've done the shuffling, we saw that the main program calls deal card to deal out the cards, and here's our deal card method. Basically, we say if the current card value is less than deck.length, that means that we haven't reached the end of the deck yet, we will return the expression deck sub card plus plus, which is going to return the card at the current card location. Then it's going to increment the current card variable after we've used its value, so that the next time we'll be looking at the next card in the deck. And if by any chance we've reached the end of the deck, we will return null to indicate that there are no more cards in the deck. So again, going back over to main, we use our new operator to create a new deck of cards. That calls the constructor and initializes the deck. We shuffle the deck, and then we walk through all 52 cards 4 at a time and deal out the cards so that you can see that they are indeed shuffled. So just summarizing a couple of the key points here. First of all, you can have an array of any type you wish as long as it's not void. So in our case, we did an array of cards. There is a difference between an array of primitive types and an array of non-primitive types. With an array of primitive types, you store the actual values of that type in the array. So an array of integers contains actual integer values. An array of booleans contains actual true-false values, etc. But if you have an array of a non-primitive type, you have an actual array of references, which are null by default, and then you have to physically assign an object to each of those reference variables in order to quote-unquote populate the array. So we did that in the deck of cards constructor, and that is one of the key things that catches most new Java programmers off guard, because they think when they create the new card array of whatever number of elements, 52 in our case, that they're actually getting card objects when indeed they are not.
Looking to advance your career by acquiring new skills? Tired of expensive off-site training programs? Wish you could learn from the best instructors in the industry? Look no further than live lessons. Self-paced, personal video instruction by the world's leading technology publishers. Each live lesson comes with a DVD featuring 3 to 4 hours of instructor-led classroom training, sample program code that allows you to work along with your personal instructor, and an example-rich study guide. Live lessons allow you to watch the entire course from start to finish, or navigate directly to any of the individual lessons. You'll literally watch over the shoulder of your instructor as he shows you how to build state-of-the-art applications. Live lessons, the power of the world's leading technology experts at your fingertips. To learn more, visit mylivelessons.com today.